Okay, thank you very much, Paul. Thank you, Lucien, for explaining everything about Institut Grand Ducal, and thank you, Paul, for the very, very precise introduction and very kind introduction as well. And thank you for everybody who decided to come. I see a lot of known faces, which makes me feel at home. Thank you very much. So today the title of the talk is Engineering Cognition, so I on purpose chose something a bit outside the beaten track because I didn't exactly know who would be in the audience. And I'll do my best to provide an overview of what we have been doing in my team for the past 20 years or so, and at the same time try to convey some messages that I think can let's say, go across different disciplines so that if you are not from any of the fields that I'm talking about today, you can still get something out of the presentation. So I'll start with a quote from Laplace, because I think it summarizes absolutely perfectly the discussion today, so which I will actually read. We may regard the present state of the universe as the effect of its past and the cause of its future. An intellect which at a certain moment would know all forces that set nature in motion and all positions of all items of which nature is composed, if this intellect were also vast enough to submit these data to analysis, it would embrace in a single formula the movements of the greatest bodies of the universe and those of the tiniest atom. For such an intellect, nothing would be uncertain, and the future, just like the past, would be present for it before its eyes. Very nice. So that's from the philosophical essay on probabilities. And so today I'll talk about almost all the salient words in that quote. So analysis, data, uncertainties, and prediction also. So therefore the future, hopefully. But there is nothing harder than to predict the future, I guess. Okay, so that's part of the team. It's impossible to depict it at any given time because there is always someone missing and there is always someone more coming from somewhere else, so it's impossible to exactly know. But these are two snippets, and as you can see, these people are coming, maybe you cannot see, but I can tell you they are coming from many different places, and a lot of them are in Luxembourg, because this is a very multicultural place where they could really find a home. So I'm very grateful to all of them, not only them, but the roughly 200 people that worked with me over the years, because without them there would be, of course, nothing to present. All right, so let's start by mathematical modeling. And today I'm going to talk about only one type of mathematical model, which assumes that you can write the problem, and don't worry, I'm not going to go into details. You can write the problem, you have a problem in front of you. We'll deal with a lot of problems in this particular talk, so I'm not going to give examples now, but you have a problem that you can write down in terms of equations. So you start assuming that the problem is a continuous problem, which is difficult to, in fact, define now in such a talk, but you will assume that the behavior is continuous, which means that the behavior at one point is very closely related to the behavior at a point which is very closely related to it in space. So if you are close in space, then you assume that your behavior will be very close to your neighbor. If you are far in space, you cannot exactly know what's going to happen. So this is as opposed to what people call discrete systems. If you, for example, think about cars being driven on a road, each car can be looked at separately, and that would be a discrete system. If you think about bats flying in some ecosystem, that each bat can be looked at separately. That will be a discrete system. And it turns out that sometimes you can model discrete systems in a continuous way. For example, you can see cars as molecules of water, and then you can model the flow of cars using the same equations as you would model the flow of water in a pipe. So that's how you can transition from discrete entities to a continuum flow, for example. So what you do in practice is you start with this, let's say, continuous problem. Let's assume that this is the assumption. And then from there, you write a mathematical model that entails equations. So this is the common way that people speak about mathematical problems. It's by writing equations. It's like a language. And from there, you revert to another discrete problem. Why do you need a discrete problem? Because you cannot, with a computer, solve an infinite problem, because the computer has a finite memory. Therefore, a continuous problem cannot be solved directly on a computer. You need to simplify it. So, for example, if I were to solve the deformation of this screen under an impact, I could not assume that there is an infinite number of points on this screen, although there is. But in practice, I will have to split that screen into sub-bits, make a grid that I will stick on the screen, and then send a basketball into it. And actually, this thing is not very deformable. Oh, it is. Send the ball into it, and then see what will be the deformation, but only at some points on the grid, or on the net that I can put there, or on the mesh that I can put there. And actually, that's the term that we use. In our field, we call things meshes. We put a mesh, like a hat you put on your head if you go in the shower, for example. Well, I don't do it apparently, but if you do that, you have a net on your head, and you can count the number of dots. Those are called nodes, and you count the number of equations that you have, and you can put that into a computer and simply invert a matrix. So if that's too fancy, you just think of solving an equation 2 times x equals 3. The question is, what is x? And then you can invert the matrix, in that case divide by 2. So if you make that multidimensional, ax equals b, where a is a matrix that is n by n, you will then look for the value at each of these little dots that are placed on the screen. So that's called the discrete problem. And then once you solve that, you get a numerical solution, and the key question everybody asks is, what is the error? So the thing on the right-hand side here, the total error. So that's usually what you see, because if I were to make an experiment with that screen and send an actual basketball in the screen and measure the deformation using a camera, for example, or 2 cameras to get a stereoscopic view, I would have an actual solution to that problem, a real solution, real life problem. And if I were to solve it numerically, I would have a numerical solution. And if I compared these two, I would get a total error, and I would be able to then validate my method, meaning that all the assumptions that I have made in the deformation of the screen, I can then now be sure that these assumptions are either right or wrong. So here on purpose I'm saying right or wrong. Usually there is no right and wrong, there is uncertainty. And then the second, so that is asking the first question, are we solving the right problem? So this is called the model error, and this measures the difference between the continuous problem, which is your view of the world, and the real problem, which is the physical problem of the screen, which exists in real life. So that's called the model error. Once you have a model and you discretize the problem, then you will commit another error, which is called the discretization error. It now assumes that the problem you assumed is correct, so the problem that you chose, the model is right, but you don't know how to solve it. You don't know if you solved it correctly. So that's called the discretization error, and that answers the question, are we solving the problem right? So there are really 2 questions. Are we solving the right problem? That's called validation. And are we solving the problem right? That's called verification. And if we can answer these 2 questions, then we know whether our numerical method is valid and verified. And now we're going to talk about this, because what is absolutely mind-boggling is that using mathematics, although you do not know the exact solution to the problem, otherwise why would you solve it with a computer in the first place, you can still give information to the user as to how accurate their solution is, although you do not know the exact solution. So this is one of the, if you don't know how it works, miracles of mathematics, that even though you don't know what the exact solution is, you can tell the user how far the solution they got is from that actual solution, which is unknown. This, if you think about it, is quite far-reaching, right? Okay, so now let's shift gears a bit from the setting, and let's try to see how we learn. So obviously, you know, I'm not a cognitive scientist at all. So what I'm talking about is what others have discovered, not what I have discovered. And in particular, if you want to learn more about this, I highly recommend you listen to the lecture series by Stanislas Dehaene at Collège de France, because he has a whole series of talks about how people learn. And this is absolutely fascinating. And this is what motivated my introduction to what we're working on. So in everyday life, you make hypotheses about the world around you, and then you compare those hypotheses to what you see. So what you see is evidence, and your hypotheses are hypotheses. They are models, essentially. And by confronting these two, you basically get a likelihood. And the likelihood answers the question, how probable are the observations given by initial hypotheses? So if I see something, so for example, if I see a car flying up in the sky, I'm going to ask myself questions because I'm not used to seeing gravity applied in the other direction. So I'm going to think that maybe I'm seeing something wrong, or something drastically catastrophic happened on Earth. So I'm going to clearly be surprised when I put the evidence and my knowledge of the world. And maybe I'm going to make a new hypothesis. So for example, when you came to this talk, many of you knew of me before, but if someone here did not know anything about me, they had no preconceived model about me. Those who did know me had a preconceived idea about who I am, how I talk, whether I'm giving good talks or bad talks, if I'm clear, unclear, fast, slow. And these hypotheses, now that you're listening to the talk, are going to be enriched by evidence, because whatever you thought before you came to this talk maybe will be changed by this actual talk itself. So you're going to confront these two, and then you're going to get a new likelihood function, and this likelihood is going to evolve with time. Let's, for example, if you, after this talk, decide to listen to another one of my talks, God forbid, then you will be maybe given the chance to get more evidence, and with that new evidence, you will change your hypotheses about the way I give talks. So this is a very simple example, which you can also think about in other terms, which are even easier to understand, I think. Let's say that you play against some Roger Federer or something, and you have observed the way that he serves. And let's say that he serves always in that area, or statistically very often in that area. Usually in the square, I would imagine. So now you're facing that person, and that person is about to throw the ball, throws the ball, starts to move the arm in a certain direction, and you know what to expect, but you see something which may contradict your expectations. Maybe his body is slightly turned in the right direction, which makes you think that perhaps the ball will not land there, but land somewhere else. So that is where the ball usually lands, and this is where it looks like it will land based on how the player actually is behaving at that very moment. And now if you look at the two together, it is going to give you an idea where the ball is likely to land, which is at the intersection between these two Venn diagrams. And this is the most plausible position of the ball, given the combination of your preconceived knowledge, which is based on facts observed on video, for example, and what you are actually looking at. So in what is called Bayesian inference jargon, because there is quite some fight between Laplace and Reverend Bayes to know who actually did what, but between the two, people believe that this is, let's not go into details, but that this is due to Bayes, but is actually based on what Laplace wrote far earlier. Which means that the posterior, which is what you know multiplied by what you think, is equal to the prior, which is the prior, what you thought before, multiplied by the likelihood, which is what you're looking at, divided by the evidence. And then that gets updated in time. So this is how it works. Every time you get new information about the world, your posterior will become your new prior. Because now that you have seen something, you have the probability of X knowing Y, which is something that we learned quite early at school, with the balls in a little urn. So there are 2 white and 2 red, and what's the probability? 2 white and 3 red, and then what's the probability that the second ball that you take out is blue, knowing that the second was red, and so on. So this is the law of conjoint probability. It is nothing different, except that what we do here is a continuous version of the ball thing, because there is a continuous event and not a discrete event, which is take the ball out. Okay, so that's actually talking about balls in urns. This is an experiment that was made by psychologists. So you see things moving around in a balloon, let's say. And you see that there are two colors, which I cannot see because I'm colorblind. So I'll let you figure out what color they are, doesn't matter. But you can see that one is outnumbered by the other, that's for sure. And so statistically, if you look at this, people obfuscate the field of view. You cannot see inside anymore, and something comes out. You will expect it to be this color and not the other color, because the other color is outnumbered by the color that just popped out. So if you do that with kids, and you actually produce these pictures in front of them, you actually see that, and this is a paper by Tiglas, which is talking exactly about the experiment and describing the experiment in detail. What you can see, and you can download it here. Oh, by the way, there will be some QR codes. You can just point your thing to this, and it should normally link you up to the papers when I refer to them, which should make it easier than copying all the data. All right, so what they actually see is this, which is that if you put a kid in front of that case, and what pops out is not this object, but the other one, which is the one that's improbable, the kid is surprised. And he or she is already surprised at the age of 12 months. So if you do that experiment with a kid that's 12 months and you show that little thing, they will show signs of surprise. Of course, maybe we cannot see because we're not trained psychologists, but that is now known as a fact. And why is that actually important? Well, because the brain is wired to learn in a way which, at least cognitive psychologists think, is a Bayesian way. So they confront their knowledge to what they see. For example, if they take their spoon with the right hand and try to eat with it, for example, they will probably paint their head with the food, and then they will stick the knife in their eye, and then finally drop the spoon on the floor with the right hand, then you pick it up, then they drop it with the left hand, and then they take it in their mouth, then they drop it with their mouth, and then every time they check that gravity does not change, whether you drop it with the right, with the left, with the mouth, if you throw it, whatever, gravity still goes down. So that's something that they establish by trial and error. And so therefore psychologists think that kids actually learn by Bayesian inference, exactly the same as Roger Federer thing that we talked about before. And what is really nice is that sometimes it's helpful to learn that way, but sometimes it's a bit, let's say, deceptive. So if you look at this picture, which is the picture of a king in England, I think Henry something, you will see that if you take the left hand side or the right hand side, for you, that person is the same. It's a three-quarter view, as people say. And this three-quarter view for you is quite identical. You will, if you see that person with the three-quarter left or three-quarter right, you will not be surprised to see that this is the same person. Which means that when you see letters like this and you try to learn, Odile or Libo is actually the same word, because in your brain, the neural activity associated with symmetry along the vertical axis is overrepresented compared to the rest, which means that you have a preconceived idea that everything that looks vertical like this, like a letter, like D, is going to be the same if you do a mirror symmetry. So you have basically to unlearn this in order to be able to learn to write properly. And that's why kids, instead of doing a D, sometimes make a B. There is nothing linked with dyslexia about this. This is just because the areas of the brain that are developed in order to recognize things that are symmetric are developed that way over generations, and therefore hamper your ability to learn to write and read. So there is a very nice paper that explains this. Lido and Obile is exactly the same word for you, because you just make a mirror symmetry of the word. So sometimes it's a bit annoying to be human, but it's also cool because, as Gopnik was saying, a baby is a scientist in the crib, and what you basically do, this is now the summary of what I just said, is that this is a hypothesis. It's not totally tested, but that the brain is able from birth, or maybe before, to perform statistical calculations, and this relies on Bayesian learning. And why is that important? Because if you go to school, and you probably see that with your kids, you constantly get grades. So this is bad. You made a mistake, -2. You made a mistake, -3. You cannot spell, -5. You cannot multiply 2 by 3, -10. Math, very important. So, and why is that wrong? Because, and Stanislas Dehaene is now on the National Committee to try to improve education in France, not surprisingly. And there it's very punitive. So it's basically, you make a mistake, it's so punitive that kids are totally scared to write anything, because anything they write is probably wrong statistically, and therefore they are worried to get a negative mark. And if you listen to Stanislas Dehaene talk, you see that this is actually counterproductive, because most of the signals in the brain are error signals, which basically are uncertainty signals. So if you block this, you basically prevent the person from learning, because it's by making mistakes that you actually learn. So there is apparently nothing new there, but for us as researchers, engineers, or whatever it is that we're doing, it's very useful to remember this, because we in fact use this in all the calculations that we do on a daily basis. All right, so now there are 5 directions that help learning. One is attention, which is what we're trying to do now, pay attention. Reward, so that's the dopamine signal that you get when you understand something. You know, you have this eureka thing, or you solve a problem, you're like, yes, I got it. Or you manage a move, anything. Curiosity, which is typically the thing that you lose when you get negative grades, when you make a mistake. Sleep, also something that we tend to lack. And error are essential to learning. So these 5 directions, that's the ones that Stanislas Dehaene is constantly repeating, are very important. And so if we summarize, why did I go through this long introduction, is because what we know about what we see around us is a model. And what I'm going to talk about are simply models. And I really wanted to explain that these models are based on observations. Whether they are observations made in a lab 200 years ago by a scientist that has his name attached, or her name, to some formula, that's one way, or maybe observations that we make today. So the first type of models are called phenomenological models, usually because they are written based on an equation that was come up by observing things for a long time. And the second are called data-driven models, and these are the more, let's say, modern ways of looking at simulations and modeling. And what we're interested in my group, but in many other groups in the world, of course, is to try to make these 2 ends meet. Data-driven models and phenomenological models written in stone. So this is what this diagram means. A model is also a function, so it takes input and it gives output. So f is a function which takes any value x and gives another value y. X can be a vector, it can be a matrix, it can be a scalar, it can be whatever you like. And there are different ways that you can do this. If you happen to be lucky enough to know something about the system you're modeling, then you maybe have equations because someone else, and one of your ancestors, wrote down some equations, like Newton, for example, and then you can use them. You can use them until they are shown wrong, of course. But as long as they are not disqualified, you can still use them. And the second thing is sometimes you have no a priori knowledge about f, about the model. So, for example, if I try to predict the probability of seeing a Coca-Cola bottle on a picture entering a bar in Belval, no one wrote down an equation for this. I mean, however, Twitter would be, or Instagram, very happy to know this because they could then sell that data to Coca-Cola to tell them, please put your, I recommend that you put your logos here and there because there is a higher probability that someone sees it, and then you will get more visibility. So that could be useful for, let's say, commerce and business. But there is no function that you can write down for that yet. Maybe one day someone can do this. So this is called data-driven model. You have huge amounts of data, because how many pictures do people take in baths? Huge numbers. You have huge numbers, but you don't know what to exactly do with it a priori. And the other counterpart would be if you send a rocket to space, you have data too, but you have also a lot of knowledge about mechanics that helps you send things flying. So this is good. And now what we're trying to do is we're trying to link the left, which is the Newton type. I had to take an example. I took Newton. I could have taken anyone else, but he's well known in his picture too. And this is a diagram of Twitter connections, which is something that you cannot write equations about. It's very messy, but it's huge. And this is the right-hand side. And now, through the rest of the talk, I'm going to give you examples where we are somewhere in the middle, sometimes more to the left, sometimes more to the right. That will depend, and we will try to see in each case how we can embrace the sort of notion of data-driven methods. Okay, so again, we said that the brain is a way to compute. It's basically a way to compute probabilities. It's a way to compute inference, to see how probable things are based on your observations. And this is what this thing talks about. And now everybody's talking not about human learning, unfortunately, but about machine learning. And machine learning everybody talks about because it's very fancy, and you have large computers, and the fact that our brain is super complicated and so on is one thing, but now people are very interested in knowing how to replicate this in terms of compute power. And in fact, that's an aside, but some computer scientists are working on chips that mimic the same type of neural patterns that are seen in the brain in order to accelerate Bayesian calculations. So that actually is new hardware that could come up to do these things. So now, what is exactly a machine learning model? Again, I'm not going to be necessarily very precise, but my goal is to convey a message. So when you have a machine learning model, what you do is you see at the bottom left a cloud of points, and you see a line that goes through that cloud of points. And the goal basically is to minimize the distance between the line and the set of points. So that's machine learning in one sentence. Very simplified. So how do you call the distance between the two? You call it the loss function, because that's what you lose. So you lose the sum of all the distances between the points. So if you've done least squares regression, this is basically least squares regression. The only difference now is the way that you minimize this loss. And this loss function here looks very simple because you have a one-dimensional x and one-dimensional y, and the number of parameters is not huge, so you can picture it in your brain. In reality, the number of parameters that you would talk about are maybe thousands. So you would have to draw points in a set of dimension 1000, like let's say r to the power 1000, and then all these points will be floating around, and you will need to let some surface or some line go through a plane, in that case a hyperplane, go through that cloud of points in dimension 100 or 1000 and minimize the distance. So that's why machine learning is not just linear regression, because there is a little bit more to that. But still the idea is exactly the same. You want to minimize the distance between ML predictions, so basically what you think, and what you see, which are the targets. Okay, so again, same idea as before. You minimize the distance between what you see and what you think is going to happen. And you do that using two approaches, which are called forward propagation and backward propagation. So first thing is you go in one direction, and then you go back in the other direction, and you minimize using some sort of descent minimization mechanism. And this is what gives you a minimum value for this loss function, and therefore allows you to optimize for the parameters, and it gives you the best set of parameters that govern the problem. This is what Saurabh did in that field. The goal, you will understand in the next example, is to predict the deformation of very soft bodies. So, for example, a soft elephant, on the right-hand side, a breast for breast cancer simulations. And the goal is to try to see if you can learn the way things deform by trying to solve a very large number of problems in that space. So, for example, you would imagine taking the elephant, pressing on its head with a load of 100 kilograms under the gravity, and then you do the same, but you push forward, then you push backward, and you, for each case, solve the problem, store that somewhere, and then you give that to the neural network, and you try to figure out if for another load, which you did not pre-compute, you're going to be able to make a prediction. And of course, as you can imagine, the answer is that you cannot if you go outside of the training range. So if you train by applying a load on the elephant which is 1 to 100 newtons, but then you apply a load of 200 newtons, which you did not pre-train for, then you're going to just extrapolate, and extrapolation doesn't work. And this is why Saurabh, in his second part of his thesis, worked on Bayesian neural nets, because in that case you can give a confidence interval knowing a prior assumption about the deformation. You can give the user a probability that the results that they will get will be within certain bounds. And that is what allows then the user to be relatively confident about the results. So that is called Bayesian neural nets, and they are actually very similar to what is done in ChatGPT. And because of that, I will make a little test now, which will test your attention, which is good because we are maybe halfway through the talk, so it's usually time when people start sleeping. So let's try to see if we can wake up. By the way, that's a very nice paper on how ChatGPT works, because that's the attention mechanism that ChatGPT relies on, the 3,000 word idea and so on. So it also makes you aware of the limitations of using this thing. All right, and this video at the bottom left explains in detail. So now focus, because it's a little game, let's say.
Count how many times the players wearing white pass the basketball. How many passes did you count? The correct answer is 15 passes. But did you see the gorilla?
You saw it? Yeah, you saw it too? Anybody didn't see it? Yeah,
This video is from research by Daniel Simons and Christopher Chabris and is copyrighted.
So
it is available for use in talks, training, and teaching on DVDs from VisCog Productions.
So beyond the little fun, it's
and
the regaining attention that we learned from this. It's really I find it very fun that our brain can actually completely separate. Once it's focused on one thing, it's a safety mechanism, because if we were to be focused on everything at the same time, then we would be incapable of doing anything. So that's a very fun mechanism, which also is related to learning, as we saw before. This is exactly what Stanislas Dehaene is saying, attention. So, okay. So what we have been working on in my team now, I would like to go a bit back in time to follow on what Paul was saying. So I did my PhD, I finished in 2003, 2004 at Northwestern, and we were working on fracture mechanics. And at the time, the basic assumptions there were that we were working with aerospace companies, and the idea is to predict if you take an aircraft and the thing starts to fly and then lands and flies and lands and flies and lands, every time you have an overpressure of the fuselage and then and then you come back to normal pressure. So you pressurize when you go up, depressurize when you go back on the ground. And if you do that sufficiently many times, it creates cracks that initiate under fatigue, and the thing just fails. And the question is, how frequently should you inspect the aircraft so that you can predict when it's going to fail? And, of course, avoid failure. And the second part was related to biofilms, because the methodology that we used for the fracture propagation was, let's say, more efficient than standard methods. I cannot go into details on this. And we tried to see if we could use it for other problems which shared mathematical similarities, like discontinuities in gradients or discontinuities in the field itself. So anything that has a front propagating, like solidification problem, nano-homogeneities, and so on, was of interest. But everything was totally phenomenological in the sense that we were using laws that were developed in the lab somewhere in the US long time ago, Paris law in that case, and there was absolutely nothing related to data here. So for example, Aravin here in the audience is working with a company here, Sisto, where they are looking at aging of rubber, and in that case he's doing himself and with other colleagues experiments on aged rubber to try to see if things fail in the same way, and he's finding very interesting results. And in that case he's basically building the next law which will be used probably for rubber failure in manufacturing in the next decades. But at the beginning there was simply no data there. So we had to rely on phenomenological models. If you cannot do that because simply things are insufficient, for example, if you know that the material that you're looking at does not fit with the experiments that were done 100 years ago by some scientist somewhere, then you need to include more information in your model. And this is what we started to do in the second third of my career, when we started working on what is called multi-scale methods. So multi-scale methods, instead of assuming things, actually go down in scale, in space or time, or both, and take into account as much of the complexities of the material or other system that you're looking at as possible, whilst keeping the computational time reasonable. So now the complexity, instead of coming from a phenomenological model, which is limited and has a lot of parameters, now comes from the actual look at the smaller scale. So if you take an example of a leaf or a tree, for example, if you want to know how much water comes out and CO2 comes in and O2 comes in and CO2 comes out and so on, if you look at a tree as one organism, then you look at it as a point. But you can also think that the tree has leaves and limbs and roots, and you can look at each of these entities as a separate entity and model it separately. So it will be a multi-scale model of a tree, and you can do that for almost anything that you're interested in. And there are ways to do that in a consistent way thermodynamically, which are very well known. And I think now what is going to be very exciting in that area is going to be the coupling between discrete and continuum systems. So for example, if we have the coupling between, let's say, discrete entities that are moving around and a continuum system that's around. For example, discrete sets of agents that are evolving in a continuum field. So this is something that I'm personally interested in, and Christian Vincenot, who just joined the university, is working on agent-based models, and I think there will be a lot of joint work there. All right, so, and then what happened is that I met a neurosurgeon, and we decided to start working on trying to help this neurosurgeon navigate during surgery. And what he told me is that it's very difficult to predict the deformation of the brain of the patient a priori, and if you didn't have any data on the fly, which means during the intervention, it was extremely tricky to figure out where things go, especially if you are inexperienced. So if you're experienced, you can train because you are used to it, so you sort of remember because you have experience, as before with Bayesian learning. But then if you do not have enough experience, it's extremely difficult to learn. And so we thought maybe we can help with that, and I'll come back to it later for the breast surgery. And in that case, we are really in between the case where we have phenomenological knowledge, because we know that the brain is made of material. Material behaves like Newton's law. essentially. It deforms under load. And it's got some inertia, some stiffness, and so on. But also, we have data that comes from the CT scans or MRIs or ultrasound that we can take during the intervention. So, and the question is, what data should we take in order to minimize the uncertainty on the predicted outcome of the surgery? And that's the question that we've been trying to ask. Okay, so now let's take one case study, which is in conjunction with the team of Alexander Skupin at LCSB on astrocytes. So this thing here is in your brain, and for a long time was thought to be totally useless. This is one of the glial cells. These are the cells that are around the neurons, and they do a lot of things for the neurons. For example, they provide structural stability, they help give food to the neurons, they help with garbage collection, and they help with other things as well. And for a long time, they were thought to be totally clueless things that are just sitting there uselessly. But for 10, 20 years, I think, it was found otherwise. And if you see these two types of astrocytes, you see quite some different structure. And the question that Sofia Farina, our PhD student, worked on was to try to figure out how important the shape of these things was on the development of neurodegeneration. So, for example, if you look at this astrocyte here, you see branches everywhere. And if you were to make a model of this, well, the first reaction would be, I cannot do this, it's too complicated, there are too many ramifications, the microstructure is horrendous, and it's extremely tough to work on. So that's why Sophia developed a new method which made that easier, to start directly from an image of an actual astrocyte, deceased or not, and was able to, okay, I have to skip this because otherwise I will never be done, was able to show numerically that there is significant differences in the way that the astrocyte metabolizes, let's say, compounds, to make it simple, in the healthy case and the deceased case. So for a bushy astrocyte, which is at the bottom right characteristic of Alzheimer's disease, you can see that the way that glucose is metabolized is quite different, and it could be inferred that perhaps this would slow the, this would actually impair the neurons, which is what you don't want if you want to avoid neurodegeneration. So this is one finding of what Sophia worked on, which is quite interesting because what in that case was done is that a real image was acquired, and then Sophia worked on a mathematical model of this actual astrocyte, making a huge number of assumptions. So again, here we are in between data-driven and phenomenological models, because as you can imagine, no one gave us the blueprints of the astrocytes, and so one, do not know the original geometry, we don't also know exactly what's going on inside. The complexity of the reactions, I think you can see here, is essentially a set of coupled chemical reactions that take place in order to provide food both to the astrocyte and to the neuron. And the question is it really the case that the astrocyte is giving the food, let's say, or the energy to the neuron, or is it keeping too much for itself? Is it too greedy? And if the astrocyte is too greedy, it may be that the neuron does not get enough energy and then starts to degenerate. One assumption, not proven, but at least in her thesis, Sophia showed that there is indications that maybe this could be linked. And as you can see, she did actual calculations on the actual shape of these things, which, I think 50 years ago would not have been very easy. Okay, and then she looked at calcium. I have to skip this, otherwise I will never be done. And I will take the second case study, which has to do with real-time simulation for surgery. So now the question is quite different. First, I will show you what Arnaud Mazier, who is the author of this PhD thesis, did when he was at the European Investment Bank for a tech fair that we helped the bank organize. So he, in that video, is taking a video of the banker, and this banker, who is in fact more an economist than a banker at the EIB, but is very happily lending himself to the game, and now can see that he has a full 3D rendering of himself, taken in a few seconds, as you can see. And then we thought, okay, maybe that can actually be used to do something useful, as opposed to scanning bankers in conferences. So that's what he did. And the reason why it's useful is the following. So if you imagine breast cancer, this is an extremely deadly disease. I'm not going to go into statistics, but it's really scary. And when that happens, the question is that you have essentially two problems. The first is that the scan is made head down, but the operation is made head looking up. So as you can imagine, once you have the preoperative image, you can figure out where the tumor is located, and you have more or less all the time in the world to do this, because the intervention is not going to be the same day. But then, when the surgery happens, the patient is lying on the back and is not actually in that position. So although you knew the position of the tumor before the operation, because you measured it in the MRI, you do not know where the tumor is located during the operation, because the circumstances are totally different. Gravity is acting relative to the breast in the opposite direction. So the question is, how can you predict where the tumor is located during the actual intervention and help the surgeon navigate, either through virtual reality or through any other means, to the right target? And so to do that, we took the patient to the space station and removed gravity, of course virtually, by inverting the mathematical problem that would deform the breast under gravity. So we assumed the patient was on the back, then took that patient to a gravity-free place, and then inverted gravity, applied gravity in the other direction, and computed the deformed version of the breast, which tells us where the tumor is located. So that sounds like, wow, so easy, such a simple problem. Okay, so why is that not easy? Because first thing is you have absolutely no idea about the material model to use for breasts. Why? Because first of all, even for the same patient, depending on the time in the menstrual cycle, the material properties will be different. The shape will be different. Size will be different. Everything will be different. So basically, at the end of the day, you do not know on day 17 whether you should use material A, B, C, combination of A, B, and C, geometry 1, 2, and 3, no idea. So you cannot also make too many experiments because you don't have so much time during the intervention, and it's quite invasive and intrusive to the patient. So you have to be quite smart in what you're doing. So this is exactly what Arno did. He had, let's call it iterative method, where the idea is to minimize the distance between what you think will happen and what you see happens. That's reminiscent, I guess. So again, you minimize distances between what you think and what you see. And you do that sufficiently fast, that's the contribution of his thesis, to be able to do that sufficiently fast that you get results in real time. So in real time you get the best model, the best parameters, and the best discretization that will give you the solution you need. And then on top of that, you can control the error on the simulation, which means you can give an idea to the surgeon how accurate the simulation is. So you can actually tell them this problem was solved with an accuracy of so many %. And what we are working on now on a new proposal with the ANR in Strasbourg is to try to help do these navigations with robots, where the navigation would be done jointly between a robot and a user. And the idea there is that the user usually is extremely good at recognizing difficult circumstances, cases which are not commonplace, cases that are rare because they have seen a lot. But sometimes maybe it could be that certain cases require extreme precision. And it could be also that the robot would then in that case be a more friendly version of a human surgeon to the patient. So the idea is that if our model were to be able to compute the uncertainty in the prediction, When the model has a huge uncertainty or large or too large, then the idea would be to tell the robot not to do anything, because the model that would be driving the robot would be mostly wrong, and to let the surgeon take over. But when the uncertainty is sufficiently low, then the robot could actually do the operation. And this combination of robot plus surgeon is also more acceptable to surgeons and also more helpful, because it allows a combination and a dialogue between the two. Okay, so this is how the computation happens. What you see is the convergence towards the actual deformed shape from the initial position, which was assumed randomly. And you can see that after a few seconds, the convergence is done and allows then the surgeon to know where the tumor is located. The next step, which I hope we can take at some point, is to do virtual reality so that the surgeon could see through and just have to simply go to the right place. Okay. Okay, so that is all, and now I will move to the third case study, which is related to what happens in your meniscus. So the meniscus is located in your knee. So if you are a runner or an ultra runner or some sort of triathlete or something, you probably know this, because it can become painful after a while, also by simply aging. That happens too. Well, aging does happen, but the degeneration of the meniscus happens also, less certainly, but does happen. And it's a little cushion in between the two bones, and you can imagine that if the cushion disappears, intuitively speaking, it's going to be bad. And it resembles, in terms of structure, a bit the discs that you have in the back as well. So it's very similar. It's a porous structure full of water, synovial fluid. And the idea, which was made originally, put out by Olga Barrera, who was a Marie Curie fellow here and also in Oxford, was to try to see if we could replicate the structure of this meniscus to make artificial ones, because at the moment it's quite difficult to replace them. Romain Zeil in Luxembourg is an expert in this, and even he says that this is not easy. So now if you look at the meniscus from close, if you do a micro CT scan, you can see that there is a huge complexity of this microstructure. If you look at the little channels here, the pores and so on, you really get a mind-bogglingly difficult version of a mathematical problem. So the idea was, let's take some microcomputer tomography, which is some way of looking at the structure of things in high detail, and let's look at this little cylinder that is taken out of the meniscus. Of course, of someone who passed away, because it's not possible to do it differently, and not ethical either. So the size, as you can see, is huge, 3 gigabytes, 5 million pixels or 6 million, and this is how the microstructure looks like. And by the way, this can be done for any type of material like sandstone. It's very useful for hydrogen storage, for example. It's a huge problem in the oil industry when people try to do fracking. So these microporous materials are not only useful in that area, but are useful everywhere where you have pores, and that is effectively everywhere. Okay, so most tissues are porous as well, not only the meniscus, but bones are porous too. And what you can do is you can look at the little channels and then try to see what happens if you coarsen them. So trying to figure out what is the impact and the importance of these little channels. And so this is what Anas Obeidat in the team here has done. So he tried to see what is the influence of the microstructure on the ability of the meniscus to propagate certain velocities. Because there is an assumption that the meniscus is there to act as a shock absorber, so that if you have high velocities, like for example you jump off the first floor on your feet, then you will have high velocity, high impact velocity, and that could damage the bone. So this is here to actually take some of this energy out. And the question is, does it come from the shape of the holes? Does it come from the connectivity of the holes? Does it come from the fluid that's inside, which is viscous? Is it a combination of all these things? Does it come from the tortuosity, the fact that these channels are not straight but running around? Where does it actually come from? And so that was the question that he asked. And in order to answer that question, what he did is he artificially created other microstructures which are not as fine as the original one, meaning that the little channels now, instead of being, let's say, 1 micron, are 1.5 micron thick, so they are wider. So you would expect that if the thing is related to the size of the channels, then you would immediately see a difference. And so let's see what we see. So these are the 3 different types of porosities that were looked at. And you see at the top the connectivity of the pores, which indicates the number of pores that a given pore in the network is connected to. So if you have a highly connected network, you will see a lot of, let's say, red, and if not, you will see a lot of blue. So now you have 3 types of porosities: high porosity, medium porosity, and low porosity for the 3 types of artificial menisci that he generated numerically. And then what you see? You see that the tortuosity is basically mostly the same. So it means that increasing the size of the channel does not change vastly the tortuosity, which was one of the assumptions we wanted to check, because we wanted to make sure that we are only changing the porosity, not the tortuosity. So there is a change, but it's not dramatic. And now the question is, what happens to the velocity that you send, let's say, inside this meniscus? So we did a computational fluid dynamics simulation of this, and we solved that using 2 different inlet pressures, one of 1.7 bar and the other of 2.1 bar, which is approximately physiological. And what you can see is a histogram of the probability of having one given velocity. So if you look at velocity 0.3, and you read off here, there are about 500, 600 points in the whole domain that had a velocity of 0.3. If you look here at the very large velocities, they are almost disappearing, meaning that the meniscus is doing something quite useful. And you see that the small velocities are passing through no problem. There are lots of points with very small velocities and very few points with high velocities. And you can see that very clearly in the case of 1.7 bar, that you have a bimodal distribution, meaning that you have first peak for very low velocity values and another round peak for, let's say, medium to low velocities. And in the second case of 2.1 bar, you can see that the high velocities are also damped because they are less frequent than the other ones. And now if you get rid of the porosity, let's say that you make the thing more porous, you also see that velocities, essentially the bottom line is that if you make the porous medium more porous, you will see that it is less effective at getting rid of high velocities than the more porous microstructure. That seems very natural, intuitive. But now we have indications, unfortunately, with only 3 different samples. We would really like to have more because it's a bit of a limitation of the work. But we hope that this will work. And you can see it here. If you have an inlet pressure in if the standard case, you see that here. But if you now kill this porosity, you see a drastic change here in terms of behavior at a certain inlet pressure value, which would indicate that there is a shift in regime after a certain porosity value. Okay, so that's the artificial menisci. Of course, we are very, very far from manufacturing any artificial menisci, because now the thing is, if we could understand what's important in the structure, we could at least replicate it using 3D printing, as opposed to simply copy-pasting menisci, which is almost undoable. So understanding would be much better than brute force. Okay, and where is that whole thing going now? Because we could do case studies all day, but let's try to see what people are thinking about. And everybody's talking about digital twins. If you go to anywhere, there is always a talk on digital twins. So a lot of funding for digital twins, but let's see what it actually means. So usually we talk about models, not about digital twins. We talk about things that are set in stone. People did experiments 100 years ago. You use it for fracture mechanics. That's a model. The other extreme we already talked about. You get into a bar, you take a picture, what's the probability of such and such things happening? A digital twin is something in between. So it's essentially a model which was made in a computer at some point, but which is talking to the real world continuously. So you can imagine this very easily by thinking of an airplane. If an airplane is flying, you can put sensors in the wing of this airplane, and in fact you do. And these sensors will spit out continuous information, petabytes of stuff that you then need to analyze to be able to figure out what is the structural health of that aircraft. Is it going to fall off the sky, or is it going to stay there for some time? And can you take off again next time, or should you leave it on the ground? So essentially what these digital twins are doing is they have an inbuilt model, again, preconceived view of the universe prior. They are fed continuous information, like our brain, and they are learning from this information in order to make a new prior, which is going to be the next model, which they are continuously updating in time. So that's a digital twin. So a digital twin is not a model fixed in space, really, nor time. It's something that evolves continuously. And I think when I read both papers and grant proposals, I tend to think that people are confusing models and digital twins. So I think it's worth repeating it as many times as possible what the differences are. And for a patient, can you imagine, if we have connected watches, we have glucose monitoring, we have all sorts of things. Soon we have Neuralink in our brain, so we can connect to the cloud or whatever. So we for sure at some point will be full of sensors if we are not already. And that will be a way to monitor your health as you monitor the health of the airplane, and to try to figure out how you could, on Earth, improve the health of that patient. There are now lots of things that are going on in that area, in particular in medicine, and this is super exciting. And I think that that it's really worth thinking about how we can have an impact on this, and also to make sure that things are done ethically and correctly, and that AI is used in a reasonable way, not in a way which is headless, like a headless chicken running around for the next buzzword, because it's quite, I think it's probably serious. It's better to be thinking about things like this, although it may be a bit disturbing. So those are a few conclusions. I try to show you a few multidisciplinary case studies where we have partial information and data on the system. I showed you how we can, in real time, assimilate data and identify material properties for breast cancer case, for example. I also showed that you can do error control and quality assurance also in real time for certain problems. And I didn't tell you that, but all these codes are open source, so they can all be downloaded and used by anybody who wants to do that. And that's it. So the case study 5 will be for another time, because otherwise there will be no time left for any discussion, which would be a shame. Oh yes, and keep this sort of attitude to life if you can, to be continuously surprised and excited about things. I think that's basically what I would like to remember if I were to remember one thing from all the interactions I had with very smart people in my team. And these are other projects that we are working on, in particular the one on Mosul with Andrea Binsfeld, who was kind enough to come tonight. Thank you, Andrea. And that Paul was mentioning at the beginning on computational archaeology, which I could not talk about today. So, thank you for your attention.
Yeah, thanks a lot, Stéphane. That was a grand overview. So we have time now for a few questions before we have a reception. Food and some drinks are waiting outside. Would anybody have a question? So I start off maybe. So you talked about learning, Bayesian learning, making mistakes. So why is it through evolution that we still do this? Because in evolution, making mistakes means death, and certainly doesn't confer a fitness advantage.
Oh. All right, so unfortunately I'm not Richard Dawkins, so I'll have to answer with my meager understanding. Well, I don't know, that's the real answer, but I also think that probably, dopamine is also what got us out of the grotto, right, to try to go and and try to explore, because every time we got a reward, we wanted to go back and get a bigger reward next time. So I really have no idea, but maybe it's related to the fact that others that did not learn as well indeed died, right?
Yeah.
And that yeah.
And reward is probably more of a selective advantage than a mistake, I guess.
Yes, probably. It's a very interesting question, actually. I have really no idea.
Okay, thanks. Any other questions? Yeah, please go ahead.
First of all, Stéphane, many things was very interesting, as well as very interdisciplinary for people in the audience. Many interesting things, as well as see that actually use quite complicated models. I guess that with the era of quantum computations, your work might be simplified. And my question is, did you already start to think in the direction of quantum computations, and did you already start to develop some quantum algorithms which could be used in your research, taking into account that just recently, a few days ago, Intel announced that they will start to sell the first 12 qubit quantum processor.
Super nice, thank you. Thank you, Fedor. So basically, I know almost nothing about quantum computing, but what I read made me exactly think in that direction. And in fact, last week I had a discussion with Christian Rasnaud, because he had the same idea for different reasons. And we thought that this is something that we definitely have to look at. For me, the reason why to look at it is because there seems to be uncertainty built in the system. And with quantum error correction and so on, it's going to be quite useful probably to think of algorithms that can use the fact that these simulations are in fact quantum, therefore that you're not sure of much, because you have these distributions of probability of energy density functions. So it could very well be, and it's exactly what I would like to do. The problem is that we would need to start with someone who in fact knows something. So maybe that's the subject of a discussion for us to have at some point.
In our group of Professor Alexander Tkachenko, who was the previous speaker, such
Yes.
event, we already have some people who work in quantum computations. Maybe our groups could collaborate on this. Thank you.
Thank you so much for the question. Yeah, very good.
Any other questions? So maybe I have another one in relation to regime shifts and porosity in relation to the meniscus. So I guess a lot of your simulations, I mean, you mentioned that you might be able to artificially produce a meniscus in the future. But I mean...
Someone, maybe.
Sorry?
Someone, I hope, based on what we do. I don't know if it will be us, but yes.
But specifically on porosity, because you mentioned that there are many other systems that are very analogous. So how, in relation to, for example, a digital twin, could you also bring the different, areas So if it is indeed in sandstone, if it is in the meniscus, how can you bring this in the form of a virtual digital twin of something that doesn't actually exist in nature, but which you could use to extrapolate how you might at least make an analog artificially?
So you mean try to look at what is common between different cases, and instead of working on each case,
bring it all together
on that and make a digital twin of this abstract version.
Exactly, like
of all these,
a virtual digital twin, or I don't know what would be.
Yeah, because then you could have quantities of interest that you could optimize for, and then try to figure out. So basically, write a generic porous medium.
Exactly. Yeah.
The most abstract version of this,
right,
and then try to optimize that, and then see which one corresponds to
which
what you
field
see
of
in nature.
application.
Yes.
Yeah.
It's a very nice idea.
And I was just thinking specifically about porosity, because that is, I guess, one of the common denominators in all of those materials.
Yes.
Cool.
That's really worth thinking about too. Thanks a lot.
Okay, sure.
3 good ideas in 2 minutes.
Okay. Any other points? Yes, please.
You mentioned the ethical consequences of some of your research. Do you think it is scientists that are best placed to sort of put the guidelines in ethical terms, or do you think it has to come from someone else?
Such a huge question. I really feel out of place to answer it, but intuitively I would say that someone, at least from outside, that does not know the science itself should be involved, but not alone, I would imagine. I would imagine that maybe an optimal way would be to have a concerted effort between people who know philosophy, have thought about philosophy of science, and others who have thought about the science itself, and try to see, because it's otherwise very difficult to disentangle the positives and negatives, like for the nuclear bomb, for example, that might have, that killed a lot of people, but maybe one could claim saved a lot of people too from another, in another way. So very difficult to know. I really don't know, but I would definitely think that yes, anthropology, ethics, philosophy, and science, let's say hardcore, I don't know how to coin it exactly, but mathematical sciences, let's say, could have to work together for sure, because it's too complex a problem to be tackled by a single discipline. And if you put scientists alone in a room, I think probably what comes out is probably unethical at some level, because of curiosity. People want to discover new things, and sometimes they are going too fast. So in particular in psychology, all the experiments that were made in the last century are really horrendous. So people being half lobotomized, others subjected to electric shocks and so on, or faking electric shocks but still thinking that so it's really worth thinking before we do any of that. And for the AI part, I really don't know really how to handle that. I think a lot of people are jumping also on the bandwagon to try to self-proclaim experts of ethics in AI, but personally I will stay away from this and say that I don't know, and that I think it's worth really thinking about what can be done and how, and also the role in education, which I think is super important. Is that going to create people that are more creative, influence people in a creative direction, or influence people in the lazy direction, or both? Is it going to create more beauty or more horror? I mean, of course, it's somewhere in the middle, but lots of questions. It's very exciting to be here now and not, super nice.
Okay, excellent. So there's, of course, food and drink outside, and that will be, I guess, fuel for more conversations. And Stéphane will be also here, so if you have any further points that you would like to discuss with Stéphane. But before we depart, I just wanted to highlight that we have again next week at the same time, same place, the next lecture in the series, and this is by Jawad Ouyaye from the Luxembourg Institute of Health and the University of Lorraine. So I hope to see some of your faces again back here at 6:30 next week. And that leaves me just to thank Stéphane again for a tour de force on all the areas that he works in, and also in particular the applications. So please give him another big hand. Thank you.